Okay, welcome to the second part of the class on Monday. And as I mentioned in the beginning of the first class, you need to join the class by clicking the link under 3.9.2. Okay, so 3.9.2 link should be clicked, and then you need to join the session. Okay. Otherwise, you might have a problem with the attendance checking. So please be careful about that. And okay, we are considering the logarithmic function. And as I said, the the logarithmic function satisfy many properties, simplifying properties. And as I said, we have this one. And as a special case, when so as I said, so log x with base a over log y with base a will be the same as log x with base y. So this is a general situation. So in when a is e, then we have ln x over ln y will be the same as log x with base y. This is one situation. And secondly, when x is a, when a, then log x with base a will be just 1, so that the equation above tells you log x with base y will be 1 over log y over x. So if you switch x and y, then you get the reciprocal, right? And in addition, you can also prove that the x log y with base a will be the same as y log x with base a. So we have this property, of course, x, y, a are all positive, and yeah, and here x and y are not one, and so on. I mean, not yeah, a, they are not one. A, x, y are not ones, but positive. Then we have this property, and so on, right? So these are some properties of logarithmic function which may be used in many examples. So I guess you are familiar with this. You already know this, I guess. And and since e is greater than 1, e to the x, e to the x is just an increasing function, so the its inverse ln x will be also an increasing function, but the graph will be just a reflection of the exponential function. So this is the graph. And okay, so those are some properties of the logarithmic functions. Now the title of the next section is the inverse of trigonometric function. Now then we have a question, we have some doubts, because what are the trigonometric functions? Sine, cosine, those functions. Now, as you remember, what is the graph of the sine function? And Moments ago, just an hour ago, I mentioned that, okay, when I consider some horizontal line, and if any horizontal line intersects the graph of the function at more than one function, then the function is not one-to-one function. So the graph of the sine function fails with the horizontal line test. Then that means the sine function, this one fails the horizontal line test. So that means this is not one-to-one function, and we can think of the inverse functions only when the mapping is one-to-one, right? And in case of the cosine, we have a similar situation. So when I draw the horizontal lines like this, then we get multiple intersections. Since the sine and cosine are periodic functions, we have infinitely many intersections. So that means the y equals cosine x is not one-to-one either. Then how about tangent? We get this increasing function between minus half pi and half pi, and then we get the same copy between half pi and 3 pi half. And then it is repeated over and over, right? So if I draw some horizontal line, then this horizontal line intersects the graph of the tangents at many points as well. So this graph of tangent function is not one-to-one. Okay, so these, and we have similar situations with the cosecant, secant, and cotangent functions. So these functions, these trigonometric functions are not one-to-one. So we cannot think of the inverse functions, right? But the problem is this. These trigonometric functions, they are used quite often in many fields of science, especially in engineering departments. You use these trigonometric functions almost in any situation. You use these trigonometric functions, and if these trigonometric functions are have some inverses, then it will give many simplification in many theories. Okay, so we want to give some exceptions on trigonometric functions. Usually, we think of the inverse functions only when the function is one-to-one, but exceptionally, with these trigonometric functions, we want to consider the inverse of trigonometric functions like sine, inverse of cosine. But since these functions are not one-to-one, we cannot think of the inverse using the standard definition. So in case of the trigonometric functions, we want to change the definition a little bit. So here's how we define the inverse of sine or cosine. And as I said, those sines and cosines are not one-to-one. They do not have the inverse of functions, but so I mean, so for example, in case of the sine function, we have this periodic function as in figure 17. So this function is not one-to-one. Okay, but as I said, we want to consider the inverse functions of this sine or cosine. So one way to define the inverse function is to make this sine function as one-to-one. And here is how we did it. If we restrict the domain of the sine function to this interval. In other words, we want to consider only this portion, okay? Only this portion between minus half pi and half pi. Then that sine function is definitely one-to-one function, right? And the range will be between minus 1 and 1. So if I restrict the domain of the sine function from minus half pi to half pi, then the range, the function will be 1 to 1, right? So this with the domain minus half pi to half pi and the range of minus 1 to 1 is 1 to 1, right? So if the inverse function of sine is needed, then people will restrict the domain of the sine function to negative half pi to half pi so that the function becomes 1 to 1. Okay? So we want to restrict the domain of the sine function from minus half pi to half pi so that the function becomes 1 to 1. Okay? And this inverse function of sine defined in this way is called the inverse sine function or sometimes arcsine function. Okay? So in your calculator, depending on your calculator, sometimes you see this notation as in f to the negative 1 to denote the inverse of sine function. But sometimes you will see ALCSIN, and that is the inverse of the sine function. So, and whenever I consider this, whenever I use this notation, whenever I use the concept of the inverse of the sine function, like arcsine is used, then we always use the restriction of the domain. Okay, so in that case, the domain of sine function will be restricted to half pi, negative half pi to half pi, so that the range of the sine function becomes from minus 1 to 1. If that's the case, then given this arcsine function, the domain will be the domain of the arcsine will be the range of the original sine function, which is minus 1 to 1, and the range will be negative half pi to half pi. So this arcsine function, the inverse of sine function, will be meaningful only under this sense, and at that point this x will be any value in the domain of arcsine, which is the range of the sine function. So x will be any value between minus 1 and 1, and at that point the corresponding y will be a value between minus half pi and half pi. So please remember that, okay? So when I just use sine function, when I use sine function, then sine of x, when I consider sine of x, x can be any real number. Okay? But sometimes I need to consider the inverse of sine function is needed. And in that case, the domain of the sine function will be automatically restricted to the from negative half pi to half pi, so that the function becomes 1 to 1. Okay. So when x is between minus 1 and 1, the arcsine function, the inverse of a sine function, will be a value between minus half pi and half pi, whose sine is x, of course. So as an example, if I want to consider this, then arcsine of 1 half will be pi sixth, because sine pi sixth is 1 half. And this pi sixth is a value between minus half pi and half pi. Okay? Please remember that the inverse function is must be 1 to 1 as well. So you have only one image for 1 half under arcsine function. And you need to choose a value between minus half pi and half pi, because the inverse function is considered only when the domain of the sine function is restricted to minus half pi to half pi. So in case of the B, arcsine of 1/3, so when I say arcsine of 1/3, it will be a value x, okay, such that this x will satisfy that sine of x is 1/3. If you consider the graph of sine function, there are many values whose y value is 1/3. But but in this equation is derived from the previous equation, which represents the inverse function. So I need to choose on x, okay, between minus half pi and half pi. So sine x is 1/3. So this x, for that x, as you can see, that is between 0 and half pi. I can consider this right triangle, okay? Then in this right triangle, the sine x represents the ratio between hypotenuse and the opposite, right? So for example, if the hypotenuse represents is say 3, then the opposite will be 1, right? If that's the case, then Pythagorean theorem says the square of the opposite plus square of the base will give you the square of the hypotenuse. So the base will be the square root of 8. So that the square root of 8 squared plus 1 squared will be 3 squared, which is 9. Or you may say 2 square root of 2 is the base of this right triangle when sine of x is 1/3. If that's the case, what will be the tangent value? Tangent value represents the ratio between the opposite and the base. So from this, the tangent of x will be 1 over 2 square root of 2, or square root of 8. Okay, that will be the tangent value. So we can find the tangent value in B when arcsine of 1/3 is given as the angle. Oops, just a second. I have, okay. Okay, the LMS server seems to be unstable at this time. So if you could not log in, please wait a minute or two and then try to log in again. Okay. I mean, because this is just the beginning of the semester and lots of students are using LMS. So the I don't know the exact reason why the server is not responding at this point, but for some students, the LMS server is not accessible. So please wait a minute or two and then please try again. Okay. And as I said, uh, today and yeah, today's class, even though you could not watch more than 90% of today's class, you won't get any penalty for today's class. Okay. So I will not give you any penalty. So you don't, please do not worry. So let me give the reply back to the students. Okay. Now, okay. So yeah, I already solved this problem. So let me go to the next one. And the cancellation equations for the arcsine function can be written by this. Okay, that is a simple relation. You, well, probably know this. Now, similarly to the sine function, sometimes I need to consider the inverse of the cosine function. Oops, okay. Inverse of cosine. And cosine function is not one-to-one either. In order to consider the inverse, I need to restrict the domain of the cosine function so that the function becomes one-to-one. Now, since the cosine function is an even function, if I restrict the domain to negative half pi to half pi, the function is not one-to-one. Instead, I need to consider a different interval, say from 0 to pi. Then the cosine function will be one-to-one as in figure 21. So when I consider the domain from 0 to 1, the function is now one-to-one. And so, so this cosine function defined on 0 to pi will be one-to-one. And at that point, the range will be between -1 and 1. So in that case, we can think of the inverse, which is denoted by this notation, or sometimes it is called arc cosine. The arc cosine of x will be y, and that is interpreted in this sense. Cosine y will be x. And when I just consider the cosine function, it is not usually one-to-one. So when I consider cosine y equals x, this y will be restricted to a value between 0 and pi. So that's what this arc cosine of x equals y implies. And the cancellation equations will be easily derived. And as I said, the cosine function, cosine x is one-to-one on the domain with from 0 to pi, and at that point the range will be the interval from -1 to 1. Then the arc cosine, the inverse of cosine is that will be 1 to 1, of course, on the with the domain from -1 to 1, and at that point the range will be from 0 to pi. To draw the graph, cosine function is a decreasing function between 0 and 1, and 0 to pi, and the range is from -1 to 1. Then when you consider the reflection, you get the graph of the arc cosine. In case of the tangent, tangent is not 1 to 1 either, but if I restrict the domain of the tangent to from negative half pi to half pi, but please note that differently from the sine function, in case of the sine function, the arc sine, okay, the sine function, it is defined on from minus half pi to half pi, including the endpoints, is invertible. But in case of the tangent function defined on minus half pi to half pi, excluding the endpoints, is 1 to 1. So this is the domain of the tangent function from negative half pi to half pi, not including the endpoints. And at that point, the range will be the whole real line from minus infinity to infinity. And when I restrict the domain of the tangent function from negative half pi to half pi, it will be 1 to 1, so that I can consider it's the inverse function. So the inverse function, or it is called arctangent, has the domain of minus infinity to infinity. That is the range of the original tangent function, and the range will be the domain of the tangent function, which is minus half pi to half pi, without including the endpoints. So we can think of the inverse of this sine, cosine, or tangent if we restrict the domain of those functions properly. Okay, so the inverse tangent function can be considered when I restrict the domain of the tangent function from negative half pi to half pi, but not including the endpoints. Okay, and it is denoted by this notation, or sometimes arctangent. So this arctangent is defined in terms of this relation of tangent function, and of course at that point this value y is restricted, okay, between minus half pi and half pi. And in a similar way, we can think of the inverse functions of cosecant, secant, or cotangent functions. And these intervals are used for those cosecant, secant, and cotangent functions, so that these functions become one-to-one on this restricted domain. Okay, so that is, yeah. So this is what I need to explain or review in chapter 1. So if we have, usually I do not review this chapter 1 though, but anyway, I just reviewed some parts, especially the last section of the inverse trigonometric functions. Yeah, so please be careful about the domains so that the functions of these trigonometric functions become one-to-one, and these domains are all different for all 6 trigonometric functions. So please be careful about this. And as I said, chapter 1 and chapter 2 review many parts of the high school mathematics. So I will go a little bit fast with those contents in chapter 1 and chapter 2. But if you have any question or if you have any difficulty with any part in chapter 1 or 2, please let me know. Okay, now we want to consider the limit of a function. So what is the limit? So given some function like this, f of x defined by x minus 1 over x squared minus 1 for many values of x and deal 1. Now, when x is 1, the denominator x squared minus 1 becomes 0 and f of x is not defined. But for all other values of x, I mean, deal 1, this function f of x can be well defined. Now, when x is smaller than 1, but if x is very close to 1, these are the corresponding function values. For x greater than 1 but close to 1, for these x values, we can evaluate f of x. So what you can observe is that as x approaches the value 1, the value of f of x seems to approach the value of 0.5. Right? So it seems that when x is very close to 1, the function value will be very close to a half. Okay, so that's what we can observe from the table. Okay, and it appears that we can make the values of f of x as close as we like to a half by taking x sufficiently close to 1. So in other words, when x is very close to 1, the value of f of x will be very close to 1/2. So for that situation, we use this notation. This notation means as x approaches the value 1, this function value seems to approach 1/2. Okay? Or people usually like this expression. We can make the values of f of x as close as we like to have by taking x sufficiently close to 1. In that case, we use this expression to describe, okay, the situation. So in general, we have the following notation. Suppose that f of x is defined when x is near some value, say a. Then, if we can make the values of f of x arbitrarily close to L as we like by restricting x to be sufficiently close to a. In that case, we use this notation to describe this event, and we say the limit of f of x as x approaches a equals L. That's how we read this expression here. Now, in this definition, please note that by restricting x to sufficiently close to a. So that means this x does not consider this, we do not consider the case when x equals a. Okay? Close to a. Okay? So we do not consider the case when x equals a. We are not interested in that part, okay? That situation when the limit is considered. Please remember, moments ago, in the previous example, we considered the limit of x minus 1 over x squared minus 1 as x approaches 1. Now, when x is 1, this function is not defined, but we do not consider that situation. We let x approach 1 as close as we want. Okay, so in the definition of a limit, okay, when x approaches a, x is approaching a, but x does not reach a. So please be careful. Sometimes instead of this notation, we may use this expression. Okay, f of x approaches L as x approaches a. And as I said, we do not consider the case when x equals a. Okay, so f of x may not be defined at that point, or may be defined. It doesn't matter. We do not care about the case when x equals a. So here in figure A, as x approaches a, so that means near a, function values are very close to the value L. In B, differently from A, the function is not defined, but near A. If I consider any point near A, the corresponding function values will be close to L. In C, the function is defined at A, but the function value at A is different from L, but we do not care about this. Okay, because when I consider any arbitrary value near A, the corresponding function value will be very close to L. So in all three cases, we say the limit of f of x is L as x approaches A. So the function may not be defined as in B, or function may be defined, but the function value at A may be different from L, but we do not care about this. Okay, so that is the case when we consider some limit of a function. So, and at that point, as x approaches A, from the left or from the right, the function value is approaching a specific value, and we could consider the limit of a function. Now, let us consider the following function h. So h function is defined for any real value t, but when t is less than 0, the function value is 0, so that the function has the value 0 for t less than 0. Now for t greater than or equal to 0, the function value is 1. Oops. So for for negative t, the function value is 0. For the positive, non-negative t, the function value is 1. Now, when I consider some t value which is very close to 0, but if it is negative, the function value will be 0. If I consider any positive t, and if it is very close to 0, the function value will be 1. Right? So depending on the side, when this t is to the left of 0, then, and if it is close to 0, then the limit will be 0. But if the value is to the right, and if it is approaching 0, then the limited value is 1. So depending on this direction, as t approaches 0, we have two different possibilities. So when t approaches 0 from the left, the function value is approaching 0 because for all negative t, the function value is 0. But if t approaches 0 from the right, then for all non-negative t, the function values are 1, so that the limited value will be 1. So depending on the side, we have different situation, different limits, and we use the following symbols to describe this. So when t approaches 0 from the left, so from the left is described by this minus sign. So when t approaches 0 from the left, the function value is approaching 0. And if t approaches 0 from the right, and that from the right is represented by the plus sign, and if that's the case, when t approaches 0 from the right, the function value is approaching the value 1. So those 0 and 1 are called the one-sided limits. That means I'm just using just one of these two sides of 0. By t is approaching 0 from the left-hand side or right-hand side. So previously, in the ordinary limit, the left-hand limit, the one-sided limits were the same, right? In the previous case, when f of x defined by x minus 1 over x squared minus 1, then at that point, limit of f of x as x approaches 0 from the left was 1/2, and the limit of f of x as x approaches 0 from the right was also 1/2. Okay, and at that point, so we simply used limit of f of x approaches 0 is 1/2. That's how we described the situation. So when these one-sided limits are the same, we could use only this simple expression, this one. Limit of f of x as x approaches 0 is 1/2. That's how we used. Okay. But in h of t, depending on the direction, okay, depending on how t approaches 0, the limited values are different. And in this case, we need to introduce these one-sided limits. So this negative sign indicates that we consider only values of t that are less than 0. That means t approaches 0 from the left. So t approaches 0 from the left. And this plus sign, okay, so indicates that we consider only values of t that are greater than 0. That means t approaches 0 from the right. So here are the definitions. So if I have this notation, I'm not sure whether you can see this negative sign. So here x approaches a with this minus. So that means my x approaches a from the left. And this notation implies that this, so that means we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to A, but I want to consider only the left hand side of A, meaning I want to consider x which are less than A. And in that case, we say we use this notation, and at that point, this L is called the left hand limit of f of x. Okay. In a similar way, this notation with a plus, that is called the right hand limit of f of x as x approaches a, and that is the case when we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to A, but I want to consider only the right hand side of A. In other words, I want to consider I want to consider x greater than A. So those will give you one-sided limits. So when I consider the left-hand limit, I do not care about the right-hand side of A. Given this A, I'm just looking at the tendency of the graph of the function f as x approaches A from the left. If the graph of the function approaches a certain number, say L, as you do this, then we use this notation with this A with minus sign. In other words, in a similar way, we use this notation with plus sign with A if the values of f of x approaches the value L as your x approaches A from the right. And at this point, I do not care about the left-hand side of A. The function may have different tendency, okay, to the left of A. It doesn't matter. Or the function may not be defined to the left of A. It doesn't matter. Okay? As long as your function values approaches the value L to the right of A, then we can use this notation to represent this right-hand limit. So those two are left-hand limit and right-hand limit. And as I said, the limit of f of x is L if and only if the left-hand limit and right-hand limit are both L's. So this limit of f of x is L implies that one-sided limits are both L's. And if the one-sided limits are both L's, then the limit of f of x will be L. Okay, so the second part of today's class lasts only for 15 minutes. So let's stop here and let's call it a day and see you on Wednesday. And as I said, for today's class, you don't have any penalty regarding the attendance. But starting Wednesday, the attendance matters. Okay? And if you have any questions regarding today's class or the previous class, last week, please email me. Okay? And if you miss any part of today's class or the last class, please email me. Okay? Okay, see you on Wednesday.